Hello, my name is Wang from University of Vienna, Faculty of Physics. Today I would like to talk about the nanoscale magnonic device from convention to inverse design magnonics. Here is our team, which is led by Professor Andrew Trumack. We also did a lot of collaboration with other universities and industries. For instance, Philip Pierre from University of Kaiserslautern, IMEC, and the Delft University. They give us the support about nanofabrication and also the information about CMOS technology. And the custom dupes, he provides us a very high quantity iron garnet. Roman Weber give us the theoretic supports. So here is our motivation of study. As you all know, the Moore's law will goes to the physics limitation. Especially in the last 20 years, the clock speed is almost constantly, mainly due to the Joule heating. So the post-CMOS technique is required, and the requirements are following the low energy consumption, CMOS compatibility, nanometer size, high frequencies. There are a lot of ways go to the post-CMOS, but one of them is wave-based computing. As you all know, in the CMOS, the information is carried by electron. So the electron only has one dimension, 1 or 0. But when we move to wave, we have two dimensions freedom. One is amplitude and another one is phase. And we also can use the furniture of waves like the interference to simplify this design of the logic gate. There are a lot of waves. Why do we choose spin wave? The first one is the low power consumption. And the second one is efficient nonlinearity. So in order to do the computing, we must use spin wave to control spin waves themselves. So this efficient nonlinearity is quite important. This is also the advantage comparing to the light, which is also another wave. And for sure, the CMOS compatibility wavelengths down to nanometer and room temperature. Before we go to the spin wave-based computing, there are several challenges. The first one is the spin wave has been well studied in macro or microstructure, but never done in nanostructure. What's the characteristics of spin wave in nanostructure? And can we develop a universal unit like a transistor in the CMOS? And which kind of physical phenomena can be used for this universal unit? And can we demonstrate an integrated magnonic circuits, which including at least two logic gates in which the magnon controlled by magnon themselves? And the last one, can we simplify the design process of the magnonic device? Follow these 4 questions. My talk has been divided into 4 parts. The first, I will briefly talk about the background of spin waves. The second one, the spin waves in nanostructure. And the third one is integrated magnonic circuits. And the last one is our recent results about inverse design magnonic device. For the first 3, if you are interested, there is a lecture on a YouTube channel which is given by Professor Andrew Trumack, Introduction to Spin Waves. You can just type the nanomagnetism and magnonics in YouTube to find this lecture. So first, the background of spin waves. Before I talk about spin wave, I want to talk about the magnetization precision. Imagine you have a spin in an external field. This spin will align along the external field. Once it moves out of the ground state, a torque will appear. This torque can be described by Landau-Lewis torque equation, and this torque will drive the spin star to precision. And in the real system, we must take into account the damping. This damping will create another torque which points to the external field and move the spin back to the ground state, like this. In the experiment, we sent an oscillation field which is perpendicular to the external field and to drive the spin star to precision. Imagine in the real materials, there are a lot of spin, thousands of the spin which is coupled by the exchange and interaction and the dipole interaction, and this precision will express as a form of wave. We call it spin wave, and we can define the wavelength and the wave number. The second one is the spin wave in nanostructure. As I mentioned before, the spin wave has well studied in the macro or microstructure, but not nanostructure. In order to understand the spin wave characteristics in nanostructure, we choose the iron garnet, which is the best materials for spin wave because it has the largest spin wave lifetime. Here is the parameter of our EEG, and the thickness is almost 14 nanometer. We fabricate one micrometer wide waveguide and the 50 nanometer wide waveguide. We use the micro-focused Brownian light scattering to detect the spin wave frequency in these two waveguides. Here is the experimental results. For 1 micrometer waveguide, the frequency is around 5 gigahertz, which is similar to the classic theory, the prediction of the classic theory. But for 50 nanometer, the experimental results is around 5.4 gigahertz. However, the classic theory gave us the prediction of 7 or 8 gigahertz, which is much larger than the experimental results. In order to understand the difference, we simulate the spin wave profile across the width of the waveguide. Please note here is the width of the waveguide for 1 micrometer. And this circle is the track of the precision of the spin. So we first extract the maximum amplitude of the precision and plot across the width of the waveguide. For 1 micrometer, we found this profile somehow partially pinned at the edge of the waveguide. But for 50 nanometer, this thing is strange because this amplitude of the precision is almost constant. So if we extract it and plot across the width of the waveguide, it's fully unpinned. This is something new compared to the microstructure here. So the spins are fully unpinned in nanoscale waveguide. And we thought if the spin has a very large precession angle at the edge of the waveguide, if we put another waveguide close to each other, what will happen? Maybe this large precession will create a dipole interaction. These two waveguides will start to talk to each other. Following this idea, we simulate this structure. We introduce another waveguide close to the waveguide 2, and we inject the spin wave only in the waveguide 2. And we found the spin wave will propagate, jump to waveguide 1 and back, forth and back, which is very similar to the coupled oscillator, the energy jump between two balls. And we also can extract the coupling length. That means the energy completely jump from one waveguide to another waveguide, this length. In order to understand the physics behind the coupling, we simulate the dispersion curve for a single waveguide here and for coupled waveguides. We found the dispersion curve split to two modes, which is called symmetry and anti-symmetry modes. Imagine we excite a frequency which simultaneously excites symmetry modes and anti-symmetry modes with different wavelengths. And due to the interference of the different modes, so the energy jump from one waveguide to another waveguide. And the coupling length can be calculated using this formula, L equal to pi over delta k. The delta k is the wave number difference between the symmetry modes and anti-symmetry modes. Once we apply an external field, shift the dispersion up or down, the coupling length will change. Or we just change the excitation frequency, and this delta k will also change, and the coupling length will also change. So following this idea, we design a magnonic or spin wave direction coupler. Here we have a very large gap in this region. The spin wave, these two waveguides are decoupled, and we use the band structure guide the waveguide into the coupled region. So as we expected, for different frequencies, we have different coupling lengths, so we can realize different functionality. For 2.88 gigahertz, all the energy goes to the signal waveguide. For 3.1 gigahertz, the direction coupler works as a power splitter, and for 3.2 gigahertz, all the spin wave energy go back to the first waveguide. If we simultaneously excite 2.8 and 3.2 gigahertz, after the direction coupler, the frequencies are separated. The direction coupler works as a frequency demultiplexer. And again, we can fix the frequency, just apply a small external field to shift the output from one to another. So The direction coupler is really a universal unit which can work as a connector, power splitter, and frequency multiplexer. So can we show integrated magnonic circuits which include at least two logic gates? Before I talk about the integrated magnonic circuits, I would like to talk about what is all magnonic circuit. Why do we need all magnonic circuits? Here is a prototype of the magnonic logic gates. It has two inputs and one output. Usually the input are current and output is spin wave. If we want to connect this logic gate to another one, we must need a conversion to convert spin wave to current. Unfortunately, this conversion will cost a lot of energy. So we propose all magnon circuits in which the inputs and outputs are all spin waves. In order to, and here we just need amplifier to bring the energy of the spin wave up to the same level of the input spin wave. So in order to realize this all magnon circuits, efficient nonlinear effects are needed, because here we need use the spin wave to control spin wave themselves. So here we choose a half adder, which is a basic element in the CMOS. So it consists of two logic gates XOR and AND logic gates. Here is the truth table of the half adder. We design a magnonic half adder which consists of 3 nanowire here and all two direction coupler 1 and direction coupler 2. Direction coupler 1 works as a power splitter. So if we have one input, half energy goes to this waveguide and half energy still in the same waveguide. The same case for the input B, half energy goes here and half energy go to here. But be careful, always shift the phase to pi to make sure here the spin wave are constructive interference and here is destructive interference. The most important part is the direction coupler 2, which work in the nonlinear region. So if we have a very low power, the spin wave will reach the output 1, but once we increase the input power, the precision angle will increase. So that means the projection of the MS on the external field direction, which called M effective, will decrease, and the dispersion curve will shift down. As we discussed before, the coupling length, which is related to the gap between the symmetry and anti-symmetry modes, the delta K. So once we shift down the dispersion curve, but the frequency is still fixed, so the delta K will change and the coupling length will change. So the output, the spin wave will reach the output 2. So the direction coupler changes the output depending on the input power. Here is the working principle of the half adder. If we have one input, half energy go to here and half energy go to the direction coupler 2, finally reach the output S. The same case for the input B, but once we have the two inputs, here is destructive interference, but here is constructive interference. So the input energy for the direction coupler 2 increased, and finally the spin wave reached the output C. So here we only have 3 nanowires, which replace 14 CMOS transistor. And here the width of the waveguide is 100 nanometer, but the whole size is comparable to the 7 nanometer CMOS technology. And also the energy consumption is also comparable, but it's slow. So, and in order to connect to next half adder, we must bring the energy of the output to the same level of the input. So the amplifier is still missing. Follow this idea, we also fabricate this direction coupler. Here the blue one is yttrium iron galate. It's a little bit larger than the simulation. It's 350 nanometer and the gap is 320 nanometer. We use a U-shaped antenna to excite spin wave here. Here is the results, which is measured by the Boolean night scattering, so the 2D map. We can clearly say for different frequencies, the spin wave the direction coupler has different functionality. And if we fix the frequency, just increase the power, we also could switch the output from one to another. So the nonlinear functionality works also in the experiment. So this direction coupler is really a universal unit which can work as a power splitter, conductor, filter, and so on. So the last part, I want to talk about our recent results about inverse design magnonics in the linear, nonlinear, and non-reciprocal functionality. This result has been published in Nature Communication. If you want to know more about this results, please visit this paper. So here we choose a very simple structure, one input and two output. We choose the width is 300 nanometer, and which is connected by a design region is 1 micro times 1 micro square meter. Again, we choose yttrium iron garnet. The thickness is 100 nanometer. Why do we choose this kind of structure? We believe that we can fabricate based on the current technology. Here we apply an external field perpendicular to the thing. So we are working for the forward volume spin waves. And we inject two frequency spin waves, 2.6 gigahertz, and the corresponding wavelength is around 2 micrometer, and also 2.8 gigahertz. The wavelength is 1 micrometer. Then we divided the design region into 100 subregions. So 10 times 10, 100 subregions. We allowed the computer to randomly remove the EEG in the design region, and we ask the computer give us this functionality, that the frequency 1 will be guided into the first output, and the frequency 2 will guide into the second output. Here is the algorithm of our inverse design. So first, we initially remove a part of the EEG in the design region, and we send this structure into the MuMax to do the micromagnetic simulation and to calculate the objective function. What's the objective function? Here the objective function is the intensity of F1 in the first output minus the intensity of the F1 in the second waveguide, and times the intensity of the F2 in the second waveguide minus the F2 in the first output. So what's the meaning of this objective function? If this objective function is notch, that means all this the frequency 1 will go to the first waveguide, and the frequency 2 will go to the second waveguide, and the crosstalk between them is minimized. So, and we calculate the objective function, and then we randomly remove one of the material, or we randomly choose one of the subregion. If this subregion is filled with materials, we remove it. If it's not filled, we filled with materials, and then calculate the objective function again. If this new one is larger than the old one, we keep it. If it's not, we undo the change, and we evaluate every subregion. So, and this is one iteration. So after 3 iterations from this picture, after 3 iterations, it's almost saturated. Here is the final results given by the computer. So here for 2.6 gigahertz, we can nearly say the energy all the energy goes to the first wave output, and for 2.8, all the energy goes to the second output. And we also took this structure and sweep the frequency from 2.5 to 3 gigahertz. We found a good bandwidth. It's around 120 megahertz. So I should to highlight this structure only optimized for 2 frequencies, 2.6 and 2.8. But finally, we will get a very good bandwidth. We use the same way to design a magnonic multiplexer, which combine 2 frequencies, two waveguides into one output. So we also get a very good bandwidth. It's around 120 megahertz. So here is the animation of the demultiplexer and multiplexer. The physics is simple. The computer designed a very complex structure, and you see for 2.6 gigahertz, here is destructive interference, and here is constructive interference. Again, but for 2.8 gigahertz, here is destructive interference, and here is constructive interference. So the physics is just interference of the waves. And as I said, we choose 300 nanometer because we believe we can fabricate nowadays. But there's no limitation of the size. We also simulate 10 times smaller 13 nanometer, and the results and the wavelengths down to 16, 17 nanometer, it still works. And in the simulation, we choose the 20 nanometer cell size, but we also check the small cell size, which works also perfect. And in the real experiment, maybe there is some overreaching during the fabrication. We also check the 10 nanometer overreaching. That means in the original design, the size is 100 times 100 nanometer square, but here is 120 times 120. So it's 40% larger than the design, but the result still works good. And finally, we also check the influence of the temperature. All this additional simulation shows the design is quite robust. Before I show you this, the inverse design linear demultiplexer or multiplexer, here we use the same algorithm, but design a nonlinear spring wave switch. Here we fixed the frequency, but we have different power, so low power and high power. We just increase the design region to 1 times 2 micrometer square, and we ask the computer to guide the low power spring wave into the first waveguide and high power spring wave to the second waveguide. But for this simulation, we simultaneously run 2 simulations with low power and high power, so we separate it. Here is the results. And for low power, all the energy goes to the first output, and for high power, goes to the second output. And we also took this design and sweep the excitation field from 0.1 to 2 millitesla. So the black one shows the output 2, and the red one shows the output 1. So we clearly see the switch between the output 1 to output 2. So the inverse design could also help us to design the nonlinear spring wave switch. And finally, we also use the same way to design a non-reciprocal magnonic circuits. In this case, we do this simulation, 3 simulations simultaneously. First, we inject the spring wave here and ask the computer guide the spring wave to here, and also simultaneously send the spring wave in another simulation, send the spring wave from the port 2 and ask computer to guide it to port 3, and the same from port 3 guide to port 1. So here is the results that the computer gave it to us. And we also took this design, sweep the frequency from 2.5 to 2.7. We still have a good almost 100 megahertz bandwidth, so it's quite robust. It's a little bit strange for us because we are working for the forward volume. As you all know, the forward volume spin wave in the frame is reciprocal. So, but where does the non-reciprocity comes from? In order to understand that, we simulate the spring wave in a single 300 nanometer width waveguide. So we excite the spring wave in the center of the waveguide, and the spring wave will propagate to the negative and the positive direction, and we extract the profile of the spin wave for negative and positive and plot it together. We see there a small shift is around 7 nanometer. That means the spin wave in the nanoscale, the forward volume spin wave in the nanoscale is not reciprocal, it's non-reciprocal. So follow this idea, we just switch the direction of the external field. Here is point out, here is point in. So as we expected, this circulation will switch. Before it's 1, 2, 3, 1, but now it's 1, 3, 2, 1. So this is really caused by this intrinsic non-reciprocal of the spring wave, of the forward volume spring wave in nanostructure. The computer just designed a complex structure somehow to accumulate the very weak non-reciprocal to realize this circulator. So the forward volume spring wave is non-reciprocal in nanoscale waveguide. Here is the conclusion. First, we start the spring wave in nanostructure to get understanding. And we design this direction coupler, which is based on To couple the waveguides based on this knowledge, we design an integrated magnonic half filter, and we realize it in experiments. And finally, we developed a new direction, which is called the inverse design methods. Thank you.